Okay, so our session 11 is being recorded now. And in this session, we will talk about two sections, infinite series and divergence test and integral test. So I'm going to start with a quick example just to kind of remind you what we're dealing with when we work with infinite series. Okay, a quick example. It's going to be example 1. Let's say we have the following infinite series. 1 over 4k squared minus 1, where k runs from 1 to infinity. Okay? Now, I have this series. We're going to break it down into several parts to kind of analyze what's going on with this series. Okay? The first thing we're going to do is to look at the first 4 partial sums. Okay? So look at the first 4 partial sums. First 4 partial sums. Okay? Sometimes it's very helpful if you just write out a couple of terms of this infinite series just to see what's happening. So what's going on here? If k is equal to 1, then we get 4 times 1 squared minus 1 in the denominator, right? Okay, so that would be 1 over 3. Okay, what about k is equal to 2? If k is equal to 2, 2 squared is 4. 4 times 4 is 16, minus 1, that's 15. Okay, so the summation says, okay, add up all of these values. So 1/3 plus 1 over 15 plus what? Okay, if k is equal to 3, we plug in 3 for k. That's 12. Oh, just kidding. That's 3 times 3, that's 9, times 4, that's 36, right? Minus 1, that's 35. Okay, and so forth. We want to know if this infinite summation, okay, does that converge? Okay, what do I mean by that? If I add up all of these fractions, infinitely many of them, do I get a finite number? Okay, that's the ultimate goal. So let's go ahead and take a look at the first 4 partial sums. And you might be asking, why 4? Well, there's really no reason. We just wanted to see a pattern and see if we can find the formula for the nth partial sum. So what is the first one? The first one is just the first term, right? So it's 1 over 3. The second one is 1 over 3 plus 1 over 15. Okay, you can simplify this. We get 2/5. The third one is the second partial sum plus that next term in the sequence. So that would be 1 over 35. You combine this, we're going to get 3 over 7. And we can do one more. So S4 is equal to S3, which is 3 over 7, plus the next term would have been 1 over 63. Okay, and if you combine these two fractions, we're going to get 4 over 9. So let me highlight these partial sums. Okay, and now put these into your sequence. So now I have a sequence of partial sums. 1 over 3, 2 over 5, 3 over 7, 4 over 9, and so forth. Okay, we say that the infinite series converges if the sequence of partial sums converges as well. Okay, so how do we determine? We need to find a formula. We need to find a formula that describes these terms as of an explicitly. Okay, so now you have enough of these values to come up with a formula. What do we have on top of the fraction? We just have 1, 2, 3, 4, and so forth, right? That's what it looks like. And on the bottom, we have 3, 5, 7, 9. All of these odd numbers starts with a 3. Okay, so then the formula for the partial sum would be what? N over 2n plus 1. Okay, now finding the limit of this is easy. Limit as n goes to infinity of this. What is the limit? What do you guys think? This one is not bad. Yeah, see somebody send a message 1/2, right? So this is 1/2. Okay, so does this infinite summation converge? The answer is yes, to 1/2. Right? Isn't that cool? All right, so you sum infinitely many numbers. Yeah, you need to kind of wrap your head around it. We're summing infinitely many numbers, but we're getting a finite value of 1/2. Okay, so here I'm going to show you following. So here's my sequence. Roughly, what are the terms here? So it's 0.33, and then 0.4 for the second one, and then 0.429. Okay, you see how it slowly grows to 1/2. The sequence of partial sums converges to 1/2. Okay, so your infinite summation is equal to 1/2. All right, so that's just a quick example to remind you the terminology, how we deal with infinite series in general. Let me stop here for 1 second. Okay, you guys have any questions? Is this okay? Any comments? Give me some indication that good, bad, it's fine.
Yeah, I'm good.
Said yes. Yeah. Okay. All right. And we keep going. Now, in this section, we're going to talk about very specific series, geometric series. What do they look like? Okay, so it's the infinite summation of the following. We have a times r to the n, right? Okay, so it's a to the first plus a r to the second plus a times r to the third power and so forth. Okay, and this is something we will need to remember, that this series converges. Okay, the partial sums converge to what? To this expression right here, a times 1 minus r to the n over 1 minus r. And this happens whenever our r, which is the ratio, is less than 1 in absolute value. So we've done it last time when we had this diagram and said, what about these geometric sequences? Okay, when do we have converges? We have converges between -1 and 1, right? Okay, so that is something that you guys will need to remember. This is one of those standard, well-established series that we need to keep in mind. Okay, so geometric series. All right, so let's go ahead and take a look at a couple of examples. So this would be your example 2 for the class, not for this particular topic. Okay, let's say I have the following setup. I have my geometric sequence. Geometric sequence with the following. A is equal to 3. R is equal to 1/2. And we start at 0. Okay, as far as the index goes. So the index starts with 0. So what does it mean? What does my sequence look like? The sequence looks like this. It's 3 times 1/2 to the 0, 3 times 1/2 to the first power, 3 times 1/2 to the second one, and so forth. That's what my sequence looks like. Okay. What about the series? The series is the summation of these, right? Okay, so the series would be 3 times 1/2 to the k. K goes from 0 to infinity. So in this case, you would be saying 3 plus 3 over 2 plus 3 over 4 and so forth. Okay, so the question is, does this series converge? And if it does, what does it converge to? Okay, all right, so what do we do? Okay, we can take a look at the sum of partial sums. So let's take a partial sums. Okay, what is the first one? The first partial sum is 3, right? And then the second partial sum is 9 over 2. Okay, so that's 4.5. And then the third one is 21 over 4. So this would be 5 1/4, right? I'm just trying to kind of estimate what's happening here. Is it growing? Yes. So partial sequences are growing. Are they going to grow out of bounds? Good question. Okay. So now we know that if r is less than 1 in absolute value, then we can do what? We can find the partial sum, the limit of the partial sum. Okay, so what would that be? Well, let's see. So let's take a look. Okay, we need to have our summation that goes from n is equal to 1 to infinity of 3 to 1/2 to the n. Okay, now we do have one of those terms, this one right here, this term 3 right here. Okay, that's not part of the formula because we need to start with n is equal to 1. So we can just simply think about it as 3 plus the summation right here. Okay, I pulled that first term out. Okay, so the index starts with 1. All right, so now we can actually see where this particular sum goes to. Where does that go to? Okay, well, we have our formula a times 1 minus r to the n over 1 minus r. Okay, that means if we plug this in, we're going to get 3 times 1 minus what? What is r? So this is 1/2 to n over 1 minus 1/2. Okay, let me stop right here for a minute. Is everybody okay with this particular part? Okay, let me see who's replying. Yes, Zachary says yes. What about the rest of you? Doug, you good? Okay. There's about 7 more people. I'm just checking.
Yep.
See if we're lost, if we're okay. Is this good so far? Okay, let me see. All right. Okay, everybody's good. Okay, so we have this expression right here. How do we deal with this? What do you guys think? Well, we can take care of the 1 minus 1/2, right? Okay, so 1 minus 1/2, that's 1/2. And if we divide by 1/2, that's equivalent to saying let's multiply by 2, right? So this is 3 times 2 times 1 minus 1/2 to the n. Okay, I want to know what the limit of this. The limit as n goes to infinity of this expression then 6 times 1 minus 1/2 to the. What do you guys think? As n goes to infinity, where does this expression go to? That's a limit, right? What does this go to? Anyone? This is not calculus 2. This is calculus 1 problem. What is it?
About
as n
sum
goes,
or just
yeah.
I'm sorry?
the limit? It's 6. It would approach 6. But the sum, yeah.
Yes. Why? Tell me why. You're correct. You're absolutely correct.
As the n power gets larger,
Yeah.
the 1/2 approaches 0, so you're essentially subtracting 0 from 1, and you're just multiplying 6 times 1.
Sounds good. Excellent. There you go. That's your whole solution. Okay? So here's your geometric sequence. We start with a geometric sequence, and then we can derive a geometric series out of it. Okay? And then you can just play with your calculator. Start adding numbers up, right? So, and you can see that we start with 3, then it's 4.5, and then we have 5.25. So it grows, but the question is, does it grow out of bound? And then maybe you do a couple more computation and you'll see that it gets close and close to 6, but it's not gonna pass 6. Okay, good. Let's take a look at another example of a geometric sequence and series that doesn't necessarily look like it's a geometric series. Okay, so here's your example number 3. Okay, so this one says following. I have a summation. K goes from 1 to infinity, e to the power negative 2k. All right, and we're going to take a look at the terms of this series. What are we dealing here with? This is 1 over e to the even power, right? So all of these powers are even. So it's 1 over e squared plus 1 over e to the 4th plus 1 over e to the 6th and so forth. Okay, now you can see that the terms of the sequence itself, 1 over e to the k, 2k, the terms will go quickly to 0, right? Okay, the terms get smaller and smaller relatively quickly. Well, the question is, what about if you add them all up? Add them all up, do we get a finite number? Okay, so now I would break this down as a geometric series. Okay, how so? My a in this case would be 1 over e squared. So I'm going to rewrite these terms as follows. Okay, so I'm going to highlight a. Okay, remember, it needs to be part of every single component in your series. And then what about my ratio, r? Ratio in this case would also be 1 over e squared, the same thing. So this is raised to the 0. This is raised to the first power, and then 1 over e squared to the second power, and so forth. Okay, so once you rewrite it this way, you can see that, oh, this is definitely a geometric series. What kind? Okay, let's write it out in a closed form. So this would be 1 over e squared times 1 over e squared to the n, and goes from 0 to infinity. Okay, so this term right here, this is what determines whether this series converges. Yes, this is our r. R is equal to 1 over e squared, definitely less than 1. We have convergence. Okay, convergence to what? Okay, so now the series converges to, and we compute it. Okay, so what is the computation there? So that would be 1 over e squared over 1 minus 1 over e squared times. Okay, so that's your setup here, right? Okay. Now we can simplify this. How do we simplify it? I'm just going to multiply by e squared on top and bottom. I will make my expression very clean. 1 over e squared minus 1. Okay? All right. You guys have any questions?
Nope.
This good? Okay. This is a finite number, right? E squared minus 1. Okay, whatever that value is, it's irrational. 1 over that, it's a small number, but it's a finite number. So let me give you a quick summary. Okay, here's your quick summary of geometric series. Okay, so what do we have? So here's your geometric series. The general form looks like this. A times r to the n. Okay. And this is equal to the limit as n goes to infinity of a times 1 minus r to the n over 1 minus r. Okay? So what things can happen? We could have r that's greater than 1 in absolute value. In this case, this limit does not exist, right? So the limit does not exist. So that means the series diverges. Okay, then if r is less than 1 in absolute value, the limit as n goes to infinity of this expression is finite. Okay, and you said if r is less than 1, that expression r to the n, that goes to 0. So we're only left with a over 1 minus r, right? So that's what it converges to. So that's a good formula to remember. Okay, and then if r is either 1 or negative 1, so in absolute value it's 1, then it's a divergent series. Which means the infinite summation is also at infinity, right? So we can keep adding small numbers, but we're going to get an infinitely big number. Okay, so that is your geometric series. Okay, geometric series. Summary of. Go ahead.
Could I see the? Could you just scroll up just a little bit so I can see the last part of it? Example 3, right there.
Yep.
That's it. Thank you.
Okay.
Yeah, I want to make sure I had that right. Go ahead. We're good. Thank you.
Yeah. Oh, this is it. So in this case, this one right here is A, right? And this one right here is R, and they just happen to be the same thing. So I'm using this formula right here, A over 1 minus R, and I can do this because 1 minus R to the n, that goes to 1 as n gets really, really large for any ratio that's less than 1 in absolute value. Okay. All right, so that's your geometric series. Another special type of series, okay, that we should be aware of is harmonic. Harmonic series is one of those that we usually introduce students with this series right here. Very simple. It's 1 over n, and n starts with 1. Go to infinity, okay? So what is this? This is 1 plus 1/2 plus 1/3 plus 1 over 4 and so forth, right? This harmonic series looks so innocent. We're adding up all of these fractions, and the fractions get smaller and smaller because the value in the denominator gets bigger and bigger, but this is divergent. Okay. this series diverges. Okay, slowly. It goes to infinity very slowly. Okay, but this sum is unbounded. Okay, now what if I just do the following? I do one simple thing, and instead of looking at 1 over n, I'm going to look at 1 over n squared. Okay, that's the only thing that I changed. So I still have 1. Now the next one is 1 over 4, and then 1 over 9, and then 1 over what? So that would be 16, and so forth. Okay, this series actually converges. Okay, and we will be able to show this. We will be able to show it with the integral test. Okay, for both of these, we have divergence in one case and convergence in the other. Okay, but harmonic series is this one right here. Very important to remember, because next week we will start talking about comparing series. Okay, and what are we comparing them to? We usually compare our series to something that's already well established. Okay, a well-established series that you know something about. So harmonic series is one of those that you want to keep in mind, that, oh, I know that this series diverges. Okay. All right. Let's see. So what else do I want to discuss before we talk about the divergence test and integral test? Alternating series.
Can I just ask a question?
Yeah, go ahead.
So whenever you wrote out the first line under harmonic series, so the summation of 1 over n from 1 to 0, 1 to infinity, well, after you wrote out the like 1 plus 1/2 plus 1/3, after you wrote all that out, someone chimed in and said that diverges, right? And you said this diverges. How do we know that diverges? Could be a
So
really stupid question. Just help me understand.
okay, so right now, just trust me.
Oh,
I know.
okay.
Yeah. So
So
in the
someone
lecture,
else chimed in and was like, "Oh, that diverges." So I was just trying to like, if I
I
was
know.
supposed
So
to
we don't
understand that, know that I didn't.
give this explanation right away.
Okay.
We just say that this is one of those things that's well established. We know for a fact that it diverges.
All
And
right.
then the integral test will also confirm that. Now, when this was discovered, first thing that was done, it was showed numerically. You know, because you can plug this in. You can plug this in, let's say, into your Excel spreadsheet. You know, plug in, 1,000 of the values. You'll see that they grow. The summation grows. It's not bounded. It's going to get bigger and bigger slowly, and slowly it's going to get bigger. But we will have a test that will show that, oh yeah, it's definitely divergent. Okay. And then the same thing for this, the second series, 1 over n squared, that one converges. Again, for now, I'm telling you that it's true. And then we will be able to match it to one of the well-established series to show why it converges. Okay? But one way to think about the convergence of 1 over n squared is the following. So we know that our harmonic series looks like this. 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, and so forth, right? Okay, so picture all of these. Now, we know that if I sum up these guys, they're going to give us infinity. But what if I just pick this one and then this one? What about next? Next one is 1 out of 9, right? So I'm just picking up these fractions right here. And then 1 out of 16, there's even a bigger gap. And then there's 1 over 25, even bigger gap. So I'm just picking values from the sequence of fractions, and the gap gets bigger and bigger and bigger. So intuitively, you can kind of see, oh yeah, we have a lot fewer numbers, right? We're adding a lot less of them. So we have a convergence here. Okay? Does that make sense intuitively? You guys see this pictorial representation of the series? Yay, nay? Are you still with me, guys? You gotta give me some indication here that I'm not talking to a wall.
Yeah, I'm here.
You're here?
I wouldn't say that it makes sense to me intuitively, but it doesn't mean it doesn't to everybody else.
Okay. Did I lose connection? Did you guys lose connection to the iPad, or do you see it?
Oh, I see a white screen. That's
No,
about
that's
it
not.
currently.
Okay, let's see what's going on. I don't want to do white screen. I want to do this. What is this? Oh, technology is failing me again. Hello. What do you guys see now? Application window. Let's take a look at this. All right, fine. Let's take a look at how can we fix this. Let's give it a minute and see if the iPad comes back. Did I get disconnected?
Well, I think we've got your computer screen.
You see an infinite loop?
Yep.
Okay. All right. Let's see what I can do about that. Do you guys hear my husband typing?
No.
I could hear
I
it.
could a little.
Okay. It's all right. Two people are working in the same house. I hope it's not too distracting. Okay, so I know what happened. My actual iPad got disconnected from the computer, which, let's see, it's fixable. Let me see if I can fix it real quick, and then we'll keep going.
Professor, I need to step away for just a minute. I'll be back.
Absolutely. Okay, how about we'll take a 5-minute break, everybody. So let me go ahead and stop the recording, and then I'll merge the two videos. So let's take a 5-minute technical break. And we're being recorded again. So for this section, what do we need to know in general? That's your quick summary, kind of like what should we focus on? Quick summary of this section. Okay. We have geometric series. Okay. Know the general form, when it converges, and what it converges to. Okay. We know harmonic series. This is your standard example of a series that diverges. Okay, this is divergent. And the last one, I haven't stated technically yet, but we're going to call the P-series. Okay, what are P-series? P-series, look of the form 1 over n to the P. Okay, not power series. So let me go ahead and make sure that we understand this is not power series, because power series is already reserved for something that we will discuss in our last chapter of the class. Okay, power series is something different. Okay, this is called P series, where P does stand for power. And where does this series converge? Okay, this converges for P greater than 1. Okay, if p is equal to 1, that is a specific example of a harmonic series, right? So 1 over n, we know that that diverges, and anything less than 1, that will also give us divergence. Okay, but whenever the power in your denominator is greater than 1, and you're doing just 1 over n, we call this a convergent series. So in general, for dealing with series, this is your question. Okay, this is your general question for the next few sections. Okay, given a series, okay, given a series, is it convergent or divergent? That's your big question. And sometimes if the series is convergent, we don't know what it converges to, but we just know that it does. Okay? Now, if it's divergent, that means it goes to infinity. Okay? So given a series, these are the two different scenarios that we can get. Okay? And also, once we get alternating series, we will talk about conditional and absolute convergence. But for now, we're just focusing in this question. If I have a series, when does it converge? What are the conditions when it converges, and what when it does diverge? Okay, so now that we feel comfortable with the whole notion of series and how to write it out and how to kind of break it down to different components, we're going to talk about the tools that are used to determine whether it's convergent or divergent. So the really big test, the divergence test. Okay, that's your first tool. There is kind of like a sequence of operations that we should apply when we're trying to determine if something is convergent or divergent, and this is your number one step. Okay, typically we will start with the divergence test. What does the divergence test say? Okay, it says the following. It says if the infinite series diverges, then the limit of the terms as k goes to infinity is equal to 0. Okay, now this statement says the following. If this series diverges, then the limit is 0. It doesn't say the other way around. What do I mean by that? It doesn't say that if the limit is 0, then the series diverges. Okay, that is not true. So this only works one way. If the series diverges, then the limit is 0. How do we actually apply? And that's the theorem, right? So what's the application? How do we apply this test correctly? Okay, we apply the following. Okay, if the limit is not 0, if the limit of ak is not 0, then the series diverges. Okay? So, what does it mean if the limit is 0? If the limit of ak is equal to 0, then the test is inconclusive. Okay, so this is important. Whenever the limit is 0, we can't say anything about it. Oh, this should be converges actually. Sorry about that. Converges. If the series converges, then the limit is 0. So what are we doing here? We're applying this opposite. If this is false, then the first statement is also false. So if the limit is non-zero, then the series diverges, which is the opposite of converges. But if the limit is 0, then the test is inconclusive. We can't come up with one conclusion or the other, which means what? We would just move on. Okay, we would just move on and say, all right, this test does not work. We need to apply something else. Okay, now let's go back to our 2 examples. My first example of the harmonic series, 1 over n, and my second example of 1 over n squared. Take a look at this. Limit as 1 over n, as n goes to infinity of 1 over n is 0, right? And limit here is also 0. So if we were to apply this test right here, the result would be inconclusive in either way. Now we know that this one is divergent, okay, right? This is diverges. This is converges. Okay, well, these are established tests, but this is to show you that if you find your limit and the limit is 0, we cannot come up with a conclusion. It can be either way. We need to do a different test. Okay. All right. So let me go ahead and show you a couple of examples where this test does work. So these are your examples for the divergence test. Okay. All right. So apply the divergence test. Okay. Let's take a look at the first one. This one says I have the summation of k cubed over k cubed plus 1, and my index runs from 1 to infinity. Okay, so what am I adding here? If I just read out a couple of terms just to get an idea, if k is equal to 1, then I get 1 over 2, right? And then k is equal to 2, so that's 8 over 9. Okay, and what about next one? That one is 27 over 8, and so forth. Okay, you will see that what you add in is a number that's kind of close to 1, but it's not really close, right? It's not very small, right? It's smaller than 1, but it's definitely close enough to kind of make you think, well, it seems like we're adding a lot. Okay, so before you even do the test, you might come up with your intuitive answer and say, we're adding all of these numbers infinitely many, and they're kind of close to 1. So if you were to add, let's say, 0.75 many times, this is divergence, right? It's going to go to infinity. So you can develop this intuition when it comes to your sequences and series in general. Now, you say, okay, let me go ahead and apply the limit or the divergence test. K goes to infinity of this expression. What do we get? What's the limit here? Okay. Anybody give me an answer? What's the limit of this expression as k goes to infinity?
Is it 1?
Yes? Why?
Because the infinity cubed is just infinity, and then infinity cubed plus 1 is just infinity, so it's infinity over infinity, which is 1.
Okay, so infinity over infinity usually is indeterminate form, right? Here we have to be.
Yeah.
Yeah, so infinity over infinity in general is indeterminate form. You can think about this as a rational function, the asymptote, 1 over 1, or if you want to be completely formal, okay, then this is 1 over 1 plus 1 over k cubed, right? I divided by k cubed. And now you know that the fraction in the denominator, 1 over k cubed, that goes to 0. So this is 1.
Okay, I'm sorry about that. But
No, that's okay. It's okay. So your intuition is maybe you say, you know what? As k goes to infinity, k cubed and k cubed plus 1 are not significantly different. And that's fine. You're right, because adding 1 doesn't really change too much. Right? But the formal write-out would be something like this. In general, infinity over infinity is indeterminate form, right? So we have to be just a little bit careful. Now, it doesn't matter. It's 1. It's not 0. That's all that matters. The limit is not 0. The series diverges. Okay? The limit is not 0. So now you might be saying, yeah, that kind of matches my intuition. Okay? That we were adding these numbers. They're not necessarily small. If we add infinitely many of them, we're just going to keep going to infinity. Okay? So let's take a look at the following example. I have summation as k goes to infinity starting at 1. And my terms look like this. K over k squared plus 1. Again, it's a good idea to write out a couple of terms. So I have 1 over 2 plus 2/5. And then k is equal to 3. That would give us 3 over 10. And so forth. Okay. 1 over 2 plus 2/5 plus 10th. Okay, so I'm inspecting these numbers. I start with 1/2, and then I go to 0.4, and I go 0.3. The next one will be 4 over 4 squared plus 1, whatever that is, right? Okay, so I'm inspecting this just to develop this intuition. What's happening here? Well, okay. Well, let's go ahead and apply the divergence test. And the problem says apply the divergence test. So limit as k goes to infinity of this expression here, k over k squared plus 1. What is the limit for this expression? What do you guys think? Finding the limit, and then we'll come up with some sort of decision. And this is a simple calculus 1 problem. What's the limit? Limit is 0. Why? You guys agree with Zachary? He says the limit is 0. He's right. Why is the limit 0?
Is it just because the bottom's going to get bigger so much faster than the top?
Yes. So you can also divide by k, right? You're going to divide by k, or you can divide by k squared. Okay. So if you want to fill in the details, this is limit as k goes to infinity, 1 over k divided by k squared. This is 1 plus 1 over k squared. This goes to 0. This goes to 0. This whole thing is 0. Okay. The limit is 0. Okay. What does that mean? What do you guys think that means?
It's indeterminate.
That's right. Well, I know what you mean. It's inconclusive, right?
Inclusive, yeah.
Yep. Inconclusive. Okay. What does it mean? Move on to the next test. We don't know it yet, but that's what you would do. Move on to the next test. Okay, whatever that might be. There are a couple of different things you could do here. All right. So, but this test does not tell you convergence, and that's why it's called divergence test. It will never tell you if something is converges. It will either tell you that the series is divergent, or it will say, oh, it's not going to work here. Try another test, try another tool. Okay? All right, so let's do one more problem for the divergence test. Let's see. Go ahead and take a look at the following. I have a series that looks like this, k over natural log of k. In my case, k starts at 2, because natural log of 1 is 0, right? And then we don't want to have a 0 in the denominator. So what do I have? I have 2 divided natural log of 2 plus 3 divided by natural log of 3 plus 4 divided by natural log of 4, and so forth. Okay, you could plug this into your calculator just to see what happens to these values. Okay, are they getting really big? You know, if they're growing, then of course the summation will also grow. But if they're small, then you might start wondering, well, okay, how small are they? Right? Okay, then we want to apply your first step. Your first step is always try the divergence test. Okay? So the limit as k goes to infinity of this expression, okay, what is it? This is infinity over infinity, which is one of those indeterminate forms. You guys remember how to deal with this? Whenever we have infinity over infinity, what's the rule that we apply here?
L'Hopital's rule.
Okay, good. We can apply the L'Hopital's rule and say, all right, let's take the derivative. Let's say this is the function of a continuous variable. If you feel like rewriting it in terms of x, that's fine. Okay, so derivative of k is 1. Derivative of natural log of k, that's 1 over k. Right? So if we simplify this, we're going to get k. Limit of k as k goes to infinity, that does not exist, right? That is infinity. That doesn't exist. Is that 0? No, that's not 0, which means this series diverges. Okay, so if I keep adding these values right here, I'm going to get infinity. All right, so here are a couple of examples. Okay, first one, we show that the limit is non-zero and it's a finite number. Finite number, non-zero. Yep, we're done. The series diverges. And we had an example where the test is inconclusive. So in this case, you would move on to another method. Okay, we don't know it yet, but we can come back to this example and solve it. All right, so inconclusive, do something else. And then here's another example where the limit does not exist. Okay, so you have infinity, either positive or negative, but it's still non-zero. It's not a finite number. In particular, it's not a 0, right? That means the series diverges. Okay, so again, I'm going to emphasize that with the divergence test, there's only 2 things that we can come up with. Divergence test results. Okay, if limit is not 0, we have divergence. If limit is 0, inconclusive. Okay, so try something else. Okay, those are the 2 things that can happen when working with the divergence test. Okay, all right. Let's see, you guys have any general questions for the divergence test? Is this okay? How do you feel about it?
It's good for me.
Yeah? Okay. What about the rest of you guys? Let me see what people are typing.
All good.
Yeah, excellent. Okay, so let's keep track of all of the tasks that we're going to go through in the next few weeks. Okay, this is going to be number 1. Okay, place to start. All right, because divergence is easier to show than convergence. Convergence you have to work with. All right, okay, so that's your divergence test. And the second test that we're going to learn this week is the integral test. Okay, so what does the integral test say? Okay, integral test. What is the general setup here? Okay, let's say we have a continuous function. F is continuous, positive, and it's decreasing. So continuous, it has positive values, and it's decreasing. Okay, for some x greater than or equal to 1. Not for some, it's just for x is greater than or equal to 1. So this is equivalent to saying my index starts with 1. Okay, you'll see the connection. And then we're going to look at a sequence such that when we evaluate it at k, at the index, we get exactly the value function, right? So k is equal to 1, 2, 3, 4, and so forth. Okay. In a way, let's say we have a sequence and we just want to rewrite it as a function with continuous increment of x instead of with k, you have these gaps, right? So k is discrete. We have 1, 2, 3, 4, and so forth. Okay. So now we're going to take a look at the integral because we know how to deal with integrals, right? And say, if the integral behaves one way, then this series behaves exactly the same way. So what's the idea here? Then the series, the infinite series of these terms, ak, and the integral, let's make sure we see the analogy. Now my limit goes from 1 to infinity of f of x dx. Okay, then they either both converge or both diverge. Okay, they act exactly the same way. Right, so that is your big statement. That's good news because what are these right here? What is this right here? It's improper integral, right? We know how to compute. That was the last section in chapter 8. Okay, it was a couple of problems on the test were to compute the improper integral. So if we show that the integral has a finite area under the curve, that means the series also converges. Okay, so let's go ahead and take a look at a couple of examples and see how we can come up with a graphical representation of what is it that we're dealing with. So here are your examples. The first one says the following. I have the summation of 1 over e to the k. K starts at 2, goes to infinity. We want to determine by applying the integral test if this series converges. Okay, so we have 1 over e squared plus 1 over e cubed plus 1 over e to the 4th. Okay, we want to apply the integral test. Okay, so we're going to consider what? We're going to consider this function f of x is 1 over e to the x or e to the negative x, right? Either way, however you like to write it, that's fine. What does it look like? Again, that's not needed for computations, the sketch, but it's not a bad idea to have this graphical representation of what it is that we're trying to find. Okay, we're trying to find the area under the curve if x starts at 2, so it's 1 over e squared. Okay, so let's say x is 2 right here. This would be 1 over e squared. We want to see if this area right here is finite. If the area is finite, then so is the sum. How so? Well, if the area is finite, then we're only adding just these values right here, right? Okay, just adding 1 over e squared plus 1 over e cubed and so forth. Okay, so we're really just taking the portion of what's already finite. It has to be finite. Okay, so then we can compute this. This is not difficult to compute. Okay, the integral from 2 to infinity of e to the negative x dx, it's the limit as b goes to infinity. This is how we approach improper integrals, right? Using the limit notation. So the limit of what? What is the antiderivative? It would be negative e to the negative x, and we evaluate it. Okay, what do we get? This would be the limit as b goes to infinity of negative, let me rewrite it as a fraction, e to the b, plus 1 over e squared. Okay, now what happens to 1 over e to the b as b goes to infinity? That goes to 0, right? This is 0. So my limit is a finite number. That is the value of this area under the curve, right? So this area under the curve. Okay, this is 1 over e squared, that whole thing. That means what? The summation of 1 over e squared, not e squared, e to the k, right? Okay, k starts at 2 and goes to infinity, is also finite. This is convergent. Not to that same value. That's not what the integral test is telling us. It does not tell us where that converges to. It just says that. Okay? Integral convergent, so is the summation. All right? What do you guys think? Is this straightforward? It's okay? What's the feel? Feeling good? Okay. All right, let's keep going then. We'll go through a couple more examples of the divergence test, and then we're actually done for the week. Okay, let's take a look at example number 2. Okay. Here, my summation looks like this. It's the infinite summation, k goes from 1 to infinity, and I have k over e to the power 2k squared. Okay, now you could apply, so let's go ahead and apply divergence test first. Okay, if you do this, you will see that the limit as k goes to infinity of this expression right here is 0. Okay, one way to think about it is that k grows, but not as fast as e to the power 2k squared. The denominator grows a lot quicker, right? So this is 0, which means the test is inconclusive. Gotta try something else. Inconclusive. Okay, so that didn't work. But okay, it's not a bad place to start. So, okay, that didn't quite work out. That's fine. We're going to consider the following function. The function, we're just replacing all of this with x. It's x divided by e to the power 2x squared. We should check that it's continuous. It is continuous because there's no division by 0 for any x, right? And no matter what I plug in there, I'm just going to get e to some positive power. So no discontinuity here. Okay, it is positive. We start at 1, all of the values that you plug in there, everything's going to be positive. Okay, it is also decreasing. And again, this is analytically, you can see that the denominator of this fraction grows a lot quicker. Okay, so all of the conditions are satisfied. We can compute the integral. The integral will go from 1 to infinity of what? So this would be x times e to the power negative 2x squared dx. Okay, so this is the limit as b goes to infinity. The integral from 1 to b, x e to the power negative 2x squared dx. And now this is a standard u substitution problem. Okay, you set up your negative 2x squared as your u, and you can see that you're going to get the following. Okay, so let me make a note here. This is a u sub problem. If you do it correctly, what you get for your antiderivative is negative 1/4 e to the power negative 2x squared. Okay, so that's your antiderivative. We need to evaluate this expression from b between 1 and b, and then take the limit this. Okay, so this is limit as b goes to infinity. What do we get here? I can rewrite it as the following. This is negative 1/4 times 1 over e to the power 2b squared. I think this way is a little bit easier to see what happens to this expression, right? Let me actually pull this negative 1/4 out. Okay, and then for the second expression, we just get what? So we get minus e to the negative 2. It does not depend on b. So this piece right here, it goes to 0. Final answer for this integral, we have minus and minus, so that gives us a plus, which makes sense. We should get a positive area. It would be positive 1 over 4 e squared. Okay, this is a finite area under the curve. What's our conclusion? And then we go back to our series. Remember, this is about our series. So this series right here, k times e to the negative k squared, it converges. Okay? We just know that it converges. We don't know what it converges to. That's sometimes, most of the time, it's not important. Okay? We just want to know the behavior of the function of this series, and it's convergent. Okay, so let me project the entire solution. There you go. So we applied the divergence test first. Doesn't quite work out. Okay, so all right, what is the other thing that we can apply? Divergence test. It is natural to go to the, not divergence test, integral test. It is natural to use that because we know how to integrate functions. The only thing that we need to make sure that is satisfied is these 3 conditions. And most of the times they will be. Okay, we'll have, just about all the time, we'll have positive functions. Continuous, okay, and then decreasing. Check that, set up your integral, evaluate it carefully, come up with a conclusion. Okay? What do you guys think? Is this all right now?
Yeah.
For me, yeah, it's a bit difficult, but it's fine.
What's the difficulty?
I don't know. It's just comprehending it. I think once I start practicing it, it'll be a lot better. But
Yeah. So you're not expected to just kind of get it immediately, right? So if this week, as you go through your homework problem, you struggle a little bit, that's absolutely normal. I don't expect everybody to just kind of say, sure, this completely makes sense, all right? And some of you will be, and if that's the case, that's great. But don't get too discouraged. if you're struggling just a little bit with this particular section, because, well, this particular chapter in general, this is the chapter that usually makes students go, oh my God, really? This is calculus too. So yeah, and the next few weeks will be kind of challenging, a little bit more challenging than you've seen before in this class. Okay, so please don't get discouraged. It's not necessarily you, it is the material itself. It's a little bit, it can be tricky. Okay, but if we try to stay focused and try to kind of break everything down and down all these different strategies, you should be able to solve all problems. Right? So let me do one more problem and then we'll call it a day. Okay? So let's see, which problem should I pick for your integral test? What's the number, for example? Example 3. Okay, so how about this one right here? We'll do the summation of the following. 1 over square root of k plus 8. Okay, it starts at 0 and goes to infinity. And you can write out a couple of terms to get an idea what is it that you're adding. Square root of 8 on the bottom, 1 over square root of 9, 1 over square root of 10, 1 over square root of 11, and so forth, right? So we're adding these fractions and they get smaller, right? They do get smaller, the fractions, because the number in the denominator gets bigger. But it doesn't necessarily mean that the summation is finite. We've seen an example of a harmonic series where this was, you know, one of those moments you're like, oh, really? This is divergent. Okay, so again, we can try the divergence test. The divergence test is inconclusive. You can see it. The limit as k goes to infinity of 1 over k plus 8, that's clearly 0. That doesn't tell us anything. Okay, so that's inconclusive. Okay, it could either be divergent or convergent. Okay, no, it doesn't work. All right, so now we're going to try the integral test. So we're going to take a look at the function 1 over square root of x plus 8. Okay, it is continuous because we start at x is equal to 0, right? So x is equal to 0 and bigger than 0. We have discontinuity at -8, but that's not in the range of values that we're considering, so we're good to go. So this function is continuous. It's definitely positive, and it's decreasing. So all of these conditions are satisfied. We're good to go to apply the integral test. Compute the integral. We go from 0 to infinity of 1 over square root of x plus 8 dx. Okay. So again, this is an improper integral. We've dealt with this concept before. Set up our limit. B goes to infinity. From 0 to b, that's the integral. Let me rewrite this as x plus 8 to the -1/2 dx. Now this integral is straightforward. You can use the u substitution. You can see the power rule will apply here. So limit as b goes to infinity. What is the antiderivative? The antiderivative is 2 times x plus 8 to the power 1/2. I'm not sure, you can check. If you differentiate this, you will get your integrand. All right, go from 0 to b. So what is the limit? Limit as b goes to infinity of this expression. So that would be square root of b plus 8 minus, if x is equal to 0, we just get square root of 8, right? Okay, but what happens to square root of b plus 8 as b goes to infinity? What do you guys think?
Becomes a larger and larger number.
Yeah, this diverges, right? This goes to infinity. So this limit does not exist. This integral is divergent. The area under the curve from 0 to infinity of this function is infinite. Okay, now that's a good, we can come up with a conclusion. The summation of 1 over, and what did I use, k? Yes, I used k. Square root of k plus 8. Okay, and k starts at 0, goes to infinity. This series also diverges. Okay, so here's your example where we compute our improper integral to get infinity. So the conclusion is, yeah, right, this is also divergent. Okay, how is this example? Let me project the whole thing. Is this okay?
Yeah, that's true.
Usually students do really well with this particular test. If you know that the function is easy to integrate and satisfies all of these conditions, then go ahead and apply it. Okay. Okay, I'm going to stop right here, and then I will stay online if for anybody that has any other questions. But we will stop right here.